1, 2, 3. That's boogie. All right, so happy return to the videos. And this video is going to be on direct proportion. So I want to do an introduction. I gave it quite a lot of thought because direct proportions are super important. So as you're kind of going through school, you're going to run into them in various formats. We don't think of them in terms of definitions, but we certainly do use them. So now these direct proportions, sometimes people call it direct variations. It just depends which textbook and author and so on that you're using. I'm going to stick to proportion, but you could just as easily use variation because it is actually a variation in terms of a change. So what are these proportions? So I'll try to illustrate it first kind of through a diagram that shows an input and then an output, which basically scales something. So that's what a proportion or variation is. It's basically just scaling an input in some way, either making it bigger or smaller. And the important thing is that it's scaling it in a constant way, right? So for instance, you can imagine, okay, so let's say this is your input. Now, in math, our input typically, we like to designate it as X. And, you have this box and something is happening within this box. And then what you have is you have an output. And for your output, what we like to do in math is we like to designate it with a Y. And I don't know what the reasoning behind this Y and X officially is. I'm sure that there are some historical reasons. I'm not the greatest in terms of a historian of maths, but X and Y are always dominant. So you have an input and an output. Now, even if you were, let's say, 10 years old and you're looking at this, you should be able to understand if I told you that, for instance, your input was this nice pink ball that was going in. All right, so let's say that is my input, and so that's my X. All right, so my X is basically this ball that is going inside, and then some magician so me, I guess, okay, you put this ball inside this box, and all of a sudden, okay, so you notice that the ball has grown. All right, so it has gotten bigger. Now, how many times did it get bigger? I mean, visually, I guess you can kind of predict, I don't know, times 3 or something, or times 4. Okay, so let's say it got bigger by 4. So here, this is basically your output Y. So just by magic, we have increased this ball coming in into, let's say, times 4. So I'm going to say that this constant, inside, it's basically multiplying, your input by 4. So if you were looking at this in terms of math perspective, so then what would have happened here is that you have, this box which is multiplying your input, X. So now in this case, your input X is your ball that is coming in. And then, so it's spitting out, and it's providing you, so it's going, spitting this out. Let's do it a little nicer here. So it's, wow. So let's do it this way. So you have that and it's spitting out your X. So this is going to be your X, and then your X just got bigger. It's basically 4 times the original ball. And the way that we like to write this in math is, instead of writing these arrows, we just simply say, all right, so your Y is equal to basically 4 times whatever your input is. So your output is equal to 4 times your input. And in proportions, so what you have is, so this 4 is basically your constant of proportion. or constant of variation, constant of variation, constant of proportion or variation. All right, so now constant because it's unchanging. So if I instead of putting a ball in there, okay, and then came along, let me remove this, okay, and instead I put a box, okay, so let's say this is my box, that was my x. Well, it's going to make the box bigger, okay, by a factor of 4, and it's just going to scale it up. All right, so it's basically unchanging. So that's what constant means there. Okay, so that's what we would have. We would have this box coming out, or like the ball coming in. So most people understand this input and output concept, right? So something grows, or it could shrink, right? So our 4 could have been 1/2. So it would make the box smaller by a half, or it could have made the ball smaller by a half. And that, what you would have is basically anything that you're putting in, okay, so anything that you would put in your box, if you would have, okay, your output, okay, and then you would try to divide your output by your input, okay, it would give you and provide you your constant, okay, so that's what would happen. Now that constant is arbitrary. I mean, I chose 4, it could have been anything. So really what we do in math, because we don't always know what that constant might be inside of that box, so we like to write y is equal to k, and k just stands for the constant of some number, and then it's scaling your input. And this right here, so what you have, okay, so right here, that scaling your k is basically what is being inputted in here inside of your box, right? So that's your k. So if you wanted to, so what we could do is, if I copy this down in here, so I'm going to take this, okay, and let me copy it and bring it down. So in general, what you have is, so we don't always know what our input is. We don't really know what's inside of this box, but what you have is basically some k. So some scaling, okay, so this is some scaling, and it is called a constant of proportionality, or a constant of variation, or constant of scaling your input, and then you get your output out. Now, where the heck does this apply in kind of real life? I mean, sure, we can scale balls, and you might be able to explain it to someone who's, 8, 9, or 10 years old, but then how does this apply in general? Well, you can think of, okay, so I'm going to put this back in here. So if I paste this back, all right, and then now what I'm going to do is kind of apply it to something a little bit more realistic. Not that scaling balls is unrealistic, because obviously it happens. It may happen if you have a toy, or it scales in terms of a house. You have a miniature house as an architect, and then you can scale it up, right? If you actually build the official house. I mean, that certainly happens nowadays, right? You have these sometimes wonderful condominiums, okay, these scales and models, and then they actually build the whole thing, which obviously is scaled quite a lot. So it's very applicable in that sense, but maybe a little bit more applicable in terms of, not necessarily scaling balls or squares or condominiums or something like that. But you can imagine that, let's say you are making money at $15 for every single hour. All right, so that's what you would have. Now, if you have a job that you're making $15 an hour, and then you have your input, well, what is your input into this box? Well, if you're working, your input is actually time. So here your x, okay, is basically time, and most likely we wouldn't write x in this case. We would have just written t for time, okay, so we can do that. So that would be your input. So now, depending on how many hours you put into your work, so let's say that you were putting in X amount of hours. So what I'm going to do now is, just so that you can see it, and we'll do a nice little table here for ourselves. Okay, so we'll do that. And so with this table, so let's divide this up. All right, so I'm going to do this. Okay, and then so this is my input T. All right, so this is where I'm inputting the T in here. Now it's going inside of my box, and let's see what happens, right, in terms of the output. Now my output is actually going to be the amount of money that you're going to make. So my input, and I'll keep it in hours. So let's say the input is in hours. So hours, I'll put H, so I'll put this in brackets in here. So you have X amount of hours. So let's say if you work 1 hour, or if you work 2 hours, or if you work 3 hours, or if you work 4 hours. Now you can so on, okay, right, depending on how many hours you have. Now the output itself, okay, is your amount of money that you're actually making per hour. And so here, so let's say the output, I'm gonna just still keep it as Y, just for the sake of this example, and it will be in dollars. So for every 1 hour you input in here, you will be making $15. So notice that 1 times 15, so here, this is gonna be $15 out, right? If you work for 2 hours, then this is going to be $30. If you work for 3 hours, it's going to be $45. 4 hours, it's going to be $60. So what we're really doing is we are taking our output now, so this, our K, which is multiplied by our input. In this case, the input is time, depending how many hours you work. So I can make this very specific to this example, where this K right here is basically $15 an hour, and it is being multiplied by the time that you're inputting in. So that's what happens. So if you take this, for example, and you substitute it in here, right, what you're doing is you're putting it into this box that you see there, and then it's just providing your output. And that is a direct proportion because it's scaling it by 15 all the time. So notice if we take anything from this, so if I take, for example, so let me make this bigger in terms of highlighting. So if I take this line where you work for 3 hours and you get 45, right? So you would maybe recall that what I said here is that, you can scale these, okay? And your constant of proportionality will come out. So y over x, okay? So if you take y over x, well, my y is 45, and then my x, okay, is 3. So here my y over my x, my input x is time. So notice, doesn't matter which line you take from here. So if I take 45 and then I divide it by 3, I will get 15, which is my constant of proportionality, right? That's what it's scaling by. If I take a different line, now it doesn't really matter which line, if I take this line and I do the scaling again, so in this case it's 60 divided by 4, notice you still get 15. That's what we mean by a constant of proportionality. It doesn't change. Constant means it's not changing. So no matter what your input is, your output will be scaled directly by this constant. Always. That's what happens. And in general, your equation that you would have is basically this equation right here, at least for this example in terms of money. Now, is that applicable to real life? Of course it is, because we all work at some point or another. I mean, some people maybe are lucky. They don't have to work on an hourly basis, which is great. Okay, but that's ultimately what you want. But at some point you probably may have to put in some time to get some money out. And so that's one example. Now, this proportionality doesn't just scale in terms of money. You can certainly scale it in many other ways. So here, if I take the example here again, okay, in terms of your inputs and your outputs, you can scale it in different ways. So one particular example could be based on concentrations. So if you have, I don't know, medication or something like that, and your medication, for instance, let's say is 10% concentrated, all right? So it's a 10% concentration of medication, right? And then the medication maybe is volume. So your input into this system, so your X, right? So let's say it's volume right here. So volume, we most likely would use V if it was in the real world. And now your output, okay, that you have in terms of the concentration would still be volume, right? But it is now, let's say, a concentration by 10%. Now, what do I mean by that? So for instance, if I gave you and I said, you know, you have a 10%, okay, let's say medication, okay, and then afterwards I would say that, all right, so let's say I have a 250 milliliter, okay, let's say an IV, right? So some IV bag which is hanging, and now it is at 10% concentration. And somebody asks you, all right, so how much medication do you actually receive? Well, most of that 250 milliliters would just be basically plain fluid of water. And then the 10% would actually be medication itself. This is also a proportion problem because you're just scaling by 10%. Now, please don't forget, you know, in 10%, so what we have is 10% as a decimal is just simply 0.1, right? Because 10% just means 10 out of 100. So here, if I would be drawing this table again, so if I take, let's say, this table, and I can kind of, let me draw another one in here. So if you have a table, okay, again, so if I draw this in here, and so for that, let me draw this in. So your input in here, so basically your input is the volume, and now your volume is in milliliters, so at least that's what I'm using here. Now your output is also volume, so it's a little bit confusing, but I mean that's okay. So I'm going to say volume as output and then volume as input in there. So let's say it's in milliliters. And now I can say that, all right, so what happens if you put in 100 milliliters in? Maybe let me get rid of these units because I did put the unit in here. All right, so it's unnecessary. So let's say 100, let's say 250 milliliters, and let's say, you know, 450 milliliters. So what would be your output, right? Meaning how much medication actually would this patient receive? So, you know, you're putting in input in here, it is 10%. So what you have is you have this Y, which is your output. So that is your volume output equals, okay, your scaling factor, your constant of proportionality is 10%. So that is 10% right here, okay, and it is 10%, okay, of your input, okay, your X. Now, 10%, I mean, if you're comfortable with percent, it's fine. But most of the time, you know, we change percents back into decimal. And then this would be multiplying your input that. So your X, okay, so that is your X, so that's your input amount of volume. Your output Y is basically your volume, okay, of that. So notice what you're going to be doing is you're going to be scaling this by this constant of 10%, which is 0.1. So if you do that, if you input 100 in here, so 100 times 0.1, well, that's going to give you just 10 milliliters, meaning that there are 10 milliliters in every 100 milliliter of that medication, right? And then if you put in 250 milliliters, then you're going to get 25 milliliters out. If you put 450, you're going to get 45 milliliters of actual medication because the concentration is 10%. And now again, okay, if you take any of these lines, so if I take, for instance, this line, and, you know, we model this in terms of Y over X. So in this case, Y over X, it's the output, okay, divided by the input. And so if I take that, so 45, which is the output, and then 450, which is the input, okay, you notice that this is 0.1, which is simply 10%. And that was your constant of proportionality. So it proportionally scaled it by 10%. And this is a medication problem, but this can also be a money problem, right? So if you're borrowing money and they're charging you 10%, You know, so for instance, if you borrowed $100, well, 10% of $100 is $10. So for every time you borrow $100, you're gonna have to, you know, kind of let them or give them back $10 of interest, for example. And that scales for many different applications. So this is just an introduction, but you should know these concepts in terms of direct proportions. So it's just a scaling factor, and you see it everywhere. And I would encourage you, you know, you can put it in the comments, you know, give me an example, put it up in the comments and say something different from here. Okay, what can be used? All right. You know, very often, for instance, you have, okay, so I'll give you one more example in here. So if I paste this, you know, a very common one. Okay, so I'll switch things up in terms of your input and output. So if you're driving in your car, right? So if you're driving in your car and then, you know, you're driving, let's say at 50 kilometers an hour. So that's what you're driving at. Okay, so that is your scaling factor. Your input, for instance, if you're driving in your car, so in this case, it would have been time. So this would be time, and it would be time in hours, okay, that we would have. And then your output, so your output in terms of this would have been distance. So how much distance do you actually cover? Okay, so if that's what you would do is, okay, so again, you know, your input, which would be time, that is your X. Your output is your distance. This is your Y. So that's what you would have there. Let me kind of make this and separate it a little bit in here. And now again, so for whatever time that you have, now notice that it has to be in hours. So if someone gives you minutes, you would have to change it to hours. So I'll keep it in hours just for the sake of simplicity. So let's say 0.5 hours. Okay, so this is in hours. Okay, the distance would be in kilometers, and I'm getting that from there, and then the hours. Okay, so 0.5, and let's say, what if you traveled, you know, 1.75 hours? What if you traveled, you know, 15 hours? Okay, so here, what our y is equal to kx equation is, okay, so our distance is our y, okay, our input is time t, and our constant is basically 50 kilometers an hour, okay, so that would be your equation, so your scaling factor by 50. So for instance, 0.5 times 50, that means you would travel 25 kilometers, okay, in that time. 1.75, so if you had 1.75, so notice 1.75, okay, so times 50, okay, is 87.5. So this is 87.5. You know, 15 times 50, all right, okay, so that would be around, I think, 750 kilometers, right? So that's what you would have there. So now again, if you take any of these, you know, you will get your scaling factor of 50. So 87.5 divided by 1.75, you will notice it's 50 because you have a direct proportion. You're directly scaling this. And this happens everywhere, okay, these proportions. Energy, it happens, you know, how much food you're intaking, okay, for example. You know, so if you're eating in and you have carbohydrates, well, carbohydrates are, for instance, 4 calories per each gram that you take. So that's another example. So every gram you take, you're going to get 4 calories. That's a direct proportion that you have. And I, again, encourage you to try to put that down. Now, the last thing that I will mention is, you know, if you take these direct proportions, what you will find with all of them, it doesn't matter what it is, and you try to graph them. So if you have a graph that you wanted to do out of any of these, so for instance, what you will find, so if this is my graph, now you may recall, so our x, okay, so that's here, so that's our independent variable, and then our y is the dependent variable. If you try to graph any of these, right, so I can take, you know, let's say I'm going to take the first one that we did here, okay, so let's copy this down, I'm going to take this one right here and copy it so that just so that you can see. All right, so I'm going to paste it back here, make it a tiny bit smaller. All right, so this is what we have. So in this case, what we have our output, okay, so our output is in dollars, and then our input is T, which is in hours. So technically, you know, I can kind of remove this X from here, and then I can put a T. And so what you have is, so this is 1, you know, this is 2, this is 3, and this is 4. Those are the hours that we had, 1, 2, 3, and 4. And then if you're graphing it up, so you're going to have, you know, so this is 15, this is 30, this is 45, and this is 60. So if time was 0, it would have started at 0, right? And then all of a sudden, what you have is you have these nice kind of plots like this, and basically, okay, you have a straight line. So, you know, these dots could come from some scatter plot, which that's what we're doing there. And then we actually have a direct line. So here you will find that every single direct proportion, this special K here, basically makes it grow. It's like a line that you will have. And of course, if we had more hours, you know, 5, 6, 7, it's just going to be a straight line, which goes through 0. Now, if you made more money than $15 an hour, then what you would find is that this line that you would be graphing would actually get steeper. And the more money you would make, okay, the steeper it would become. So, you know, you can keep drawing these, and these would be getting steeper and steeper, okay, depending on how much money you make per hour. And if you make less per hour, then this line would get, you know, less steep. All right, because it would take you a lot longer to make the same amount of money. So that's what I wanted to mention in this video, and hopefully you get this concept of direct proportion nicely scaling through. All right, and I always think of it, you know, kind of all the way back, you know, here with what we started originally with that ball or that square, where it's just a scaling of something that happens, and that scaling is constant. All right, depending on the application you have. Okay, so thank you for watching. That's the introduction to these. I'm going to continue on, so we'll have some other ones in terms of the various scalings that you have. Okay, so cheers, okay, and we'll see you in a future video. Bye.